Okay, so we'll discuss what is Newton's method first of all. Okay, so the idea is you are given a function f of x, and you want to find out what is the zero of this function. Namely, what should I substitute for x so that I get output as zero? Say, for example, if I'm asked f of x, if I'm given f of x equals to, say, x squared minus 1. So if I'm asked about what is the zero of this function, then it's clear. Zero of this function is, say, f of 1 is a 0, which is 1 squared minus 1, that is 0. Or f of 1 is minus 1 is 0, right? So these are the zeros of the function. So this is this is what Newton's method does. If you're given a function f of x equals to 0, it will try to find out the zero of that function. So let's see how it works. Um, so so suppose you have a suppose you have a function like this. Say y equals to f of x. And what you really want is the zero. So zero is over here, right? So this is your zero function. So what you do is you start with any point x0 of your choice. Generally, there's a better way to do that, but if you start with x0 of your choice, then what you can do is you can draw a tangent line at x0. And suppose this tangent line cuts your graph at, so suppose this tangent line cuts your x-axis at x1. So this is your new iteration. Then what you do is you again go back on the graph. This point is going to be x1, f of x1. You draw a tangent line there. You draw a tangent line there and cuts your graph x-axis at x2. And as you can see, x0, x1, x2, they are getting slowly closer and closer to the, then you again do this, and again you get closer to your what? To your solution, which is x. Okay, so this process is called Newton's method. All right, so let's see, how do you compute? So you start with an x0, which is good enough choice. And then how do you compute from x0? You compute x1. So first of all, notice that this line here is a tangent line at x0. So what is the equation of tangent line at x0? y minus, sorry, y minus f of x0 equals to f prime x0 times x minus x0. So this is the equation of tangent line for the first one, right? So for here, if we draw the tangent line, this is the equation of this tangent line is given by this, right? Now, where it cuts the x-axis, if it cuts where it cuts the x-axis, you're choosing to call that value of x as x1, and where it cuts the x-axis, your y will become 0, right? So substitute this here. So you get minus f of x0 equals to f prime x0. Your x became x1, so minus x1 x0. So now from here, if you divide that f prime x0 on the other side, you get f of x0 divided by f prime x0. And bring that x0 on the other side, it's minus, so it will become plus here. equals to your x1. So you see, using x0, you get x1. Similarly, you can repeat this process. You can get x2 from x1 in the same way, exactly the same process, right? Drawing the tangent line and seeing where it cuts the x-axis. So the formula is going to be exactly the same. Right? In fact, you can keep on repeating this process and you will have x1, x2, x3, blah, 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 all the way until you keep on repeating up to the approximation you really want uh, by using the following. F of xn, sorry, xn plus 1 is xn minus f of xn divided by f prime of xn. So this is called Newton's method. All right, so this is the Newton's method. So again, the idea is you start with the initial guess of your choice. Here, I mean, like some people say x1, x0, doesn't matter, right? What you're starting with, whatever you want to call the starting point as. So here we're calling the starting one as x1. So you can get x2 out of x1 by the following. X2 is x1 minus f of x1 divided by f prime of x1. And similarly, you can keep on going this process and you get xn plus 1 is xn minus f of xn divided by f prime of xn. All right. So let's look at the following problem. So solve 5x plus cos x equals to 5 for x belonging to 0, 1, correct up to 6 decimal places. So now what does it mean by correct up to 6 decimal places? That the 6 decimal places, basically, it should be correct up to 6 decimal places. And the way you find out is the following. If you look at an iteration, say, suppose you have iteration xk and xk plus 1, if they are equal up to 6 decimal places, then you say your answer is correct up to 6 decimal places. Okay, so now let's try to do this problem. So first we'll make f of x out of it. So the function we want to solve for the x here, so essentially we are looking for, take f of x to be 5x plus cos x minus 5, right? So solving an x, sorry, finding an x which satisfies this equation now has converted to a problem of root finding for this. Okay. So let's set up the Newton system. So Newton's formula. Note that it's also called Newton-Raphson method. Okay, so there were two mathematicians, Newton-Raphson. So some people just choose to call it Newton's formula, and other people, like some people, try to call it Newton-Raphson method. Okay. So you have to set up. You have xn plus 1 equals to xn minus f of xn divided by f prime of xn. So this is going to be xn minus f of xn, which is 5 xn. I need to keep this in bracket because the minus sign outside, cos of xn minus 5, the whole divided by derivative of this, which is going to be 5 minus cos, sorry, derivative of cosine is sine minus sine. So we have sine xn. Okay. So now you have to start with the choice of x0. Now you're not given x0, right? So, but you're said solve for this in x belonging to this 0 to 1. So the 0 must lie inside this, isn't it? So let's take x0 to be something in 0, 1. What inside 0, 1? It doesn't matter. All right. So choose anything inside 0, 1. And so let's say x0 to be 0.5. Yeah. So then x1 is going to be 0.5 minus 5 times 0.5 plus cos of 0.5 minus 5 divided by 5 minus cos of sine of 0.5. Okay, so now can you compute this? So you can use your calculator to compute this. So we found out that so x1 is going to be, when you do the computation, is going to be 0.858896. 1, 2, 3, 4, 5, 6, 6, 2. Then you use this to compute what? X2. Your x2 turns out to be 0.8712098223. And then you can look at your x3, which is going to be 0.87122115. 2, 3, 4, 5, 6, 7. I'm listing only 7 decimal places because I want accurate up to 6 decimal places. So I will stop when, and then you see that x4 is going to be 0.87122215. All right. So x3 and x4. So the solution is going to be 0.871221, accurate up to 2 decimal places. Sorry, accurate up to 6 decimal places. So this is how the whole thing works. Now let's look at the other problem. Use Newton's method to find square root of 2 accurate up to 8 decimal places. We'll just do up to basically 3 decimal places. All right, we don't want to. So how do we go about it? First of all, we need a function, right? Here, we don't know what is the function, right? So we want to encode root 2 as a 0 of some function. So what function it can be? So if you look at this guy, x equals to root 2, this would mean x squared minus 2 equals to 0. So we have found out what function we are looking for. So f of x is going to be x squared minus 2. So set up the Newton system. So x to the n plus 1 equals to xn minus f of xn divided by f prime of xn. So this is going to be xn minus xn square minus 2 upon derivative of that which is 2xn. So this is your Newton system, but we can simplify it further. So it's going to be 2xn square minus xn square plus 2 divided by 2xn, which is going to be xn square plus 2 divided by 2xn. Now you may wonder, why did I simplify it? Notice that in the previous one, you had 1, 2, 3 places to put xn. Now you have 2 places to put xn. So there is, the lesser the places of where you have to substitute xn, the better or robust the algorithm is going to be, right? Because otherwise you'll have 3 places where if you do approximation for this, approximation for this, approximation for this, there will be 3 places where the errors can come in. Here in this case, there are only 2 positions where you will have approximation. So it's better. So now let's choose. So we are not given x0. So let's take x0 equals to what? Now we have an idea about how square root of 2 is, right? It's roughly 1.41 something, right? So we'll come something which is close to square root of 2. Now note that if you have no idea about your 0 of your function, you have to use intermediate value theorem to get some idea about it, right? Sometimes you can start even without knowing what is a 0. And if the function is nice enough, there'll be a convergence. So let's see the following. So we'll take x0 to be, say, let's start with 1. Yeah. So then what do we get? X2 is, sorry, x1 is x0. So I'll be substituting x0 in this equation. So x0 squared by 2 divided by 2 x0, that is going to be, so x0 squared by 2, so let's substitute, we get 1 plus 2 divided by 2, which is going to be 3 by 2, which is 1.5. So let's try the next one now. So we have x2 is x1 square plus 2 divided by 2x1, which is going to be 1.5 square plus 2 divided by 2 times 1.5, that is going to be 1.5 square is 2.25. So let me do this calculation on my computer here. Calculator. So I have x plus 2 by 2 times. So I'm doing this on my computer, this calculation, so it will take a minute. So 3 by 2. So when I start with the 3 by 2, I get, my next iteration is going to be 1.41666. Okay, so since I'm only looking for up to 3 decimal places, I can just worry about until here. Similarly, when I find my x3, I need to substitute x2 in this equation, and the answer turns out to be 1.4166. So I substitute this, and my next answer is 1.4142. You see, now it's already what? So if I was asked do up to 2 decimal places, accurate up to 2 decimal places, I will stop because the first 2 decimal places have become equal. But since I'm asked about 3 decimal places, I'll go for x4 now, and x4 is 2. When I do compute for x4, I get again 1.412. So you see, this is accurate up to, so this is accurate up to 3 decimal places. Yeah, so my x is 1.414. Okay, so this is how the Newton's method works, right? So now let's look at the following problem. Use Newton's method to solve for x to the power 1 by 3 equals to 0 by taking x0 equals to 1. So again, we have f of x equals to x to the power 1 by 3. Then what do we have? What is the Newton system going to be? Xn plus 1 equals to xn minus f of xn divided by f prime of xn. Now this is going to be xn minus f of xn is, what is f of xn? X to the power 1 by xn to the power 1 by 3. What is f prime? So derivative of this is f prime of x is 1 by 3 x to the power minus 2 by 3. So this is going to be 1 by 3 x to the power minus 2 by 3, and that simplifies as x to the n minus xn to the power 1 by 3. Dividing by 3 is multiplying by, dividing by 1, 3 is multiplying by 3. This will go on the top, so it will become, so this will become minus 2 xn. So xn plus 1 is minus 2 xn. So let's see. So if you start with x0 is 1, your x1 is minus 2 times x0, which is minus 2. Similarly, your x2 is minus 2 times x1, which is 4. x3 is minus 2 times x2, which is minus 8. And so on and so forth, right? So you see that instead of getting closer and closer to any solution, the only zero of this function is this is a zero of your function. Zero is zero. But instead of going closer to the solution, because of the shape of this, the tangent lines are kind of moving away, right? So instead of getting closer and closer to solution, you're getting further and further away. So this gives you an example where Newton's method fails. Okay.
One
Now,
question. Sorry. Is there a test or a way to know where it fails? Newton's method?
that depends on the shape of your graph, right?
Just the shape. Okay. And then the other thing is, do we have to show for like when
So here, so f of x equals to x cubed plus 3x plus 1, show that it has exactly one root in minus half to 0. So generally you discuss the intermediate value theorem on closed interval, but here it's fine as long as you do not get zeros at these, right? So first of all, f is a continuous function. And f of minus half is what is f of minus half? It's going to be minus half cube plus 3 times minus half plus 1, which is going to be minus 1 by 8 minus 3 by 2 plus 1. And then when you combine these two together, you'll get minus 1 by 8 minus 1 by 2, and that is less than 0. Similarly, f of 0 is 1, which is greater than 0. Therefore, by intermediate value theorem, f has at least 1, 0 in minus half to 0. Okay. However, it says that we want to show that it has exactly 1, 0. So how do we go about it? So there are various ways. One way is to use is mean value theorem. The other one is the following. Look at the derivative of this function. So if you look at the derivative, it's 3x squared plus 3, and that is greater than 0 on minus half to 0. Right? It's actually greater than 0 everywhere, but particularly it's greater than 0 on minus half to 0. What does it mean? It means that f is an increasing function. F is an increasing function, therefore what? Therefore, the graph of f of x can cut x-axis at most once, right? If something is increasing function, it can only cut the x-axis at most one. So at most once and at least one makes it what? Exactly one. Therefore, f cuts x-axis exactly once in minus half to 0. Therefore, f has exactly one root. Yeah, I should basically write it with the round bracket to make it clear that the 0 is inside. Okay. So now the question is so now the next part of the question, use Newton's method to find out the root that lies in minus half to 0. Stop when the next iteration agrees with the previous one up to 4 decimal places. So now in this case, we have to set up the Newton system. So B, Newton's formula is xn plus 1 equals to xn minus f of xn divided by f prime of xn. So this is going to be xn minus f of xn, which is xn cube plus 3xn plus 1 divided by derivative of this, which is 3xn square plus 3. And you can simplify it further, cross multiply and simplify, so you get 3xn cube plus 3xn minus xn cube minus 3xn minus 1 divided by 3xn squared plus 3. So you can notice that few things will get cancelled off, this guy and this guy, and you'll have 2xn cube minus 1 upon 3xn squared plus 3. Now note that you don't really need to do this for our course purpose, but in real life scenario, you want to minimize the number of errors in your computation. Okay, so in real life scenario, you'll have to basically, it's a good idea to basically reduce the number of places where you have to substitute your xn. Okay, so all right, so let's move ahead. So now you can take x0 to be any number of your choice. You could have chosen minus half or 0. I will rather choose it to be something in between of it, which is minus 1 by 4. And then from there, so this is minus 2.5. Now from there, can you compute x1? So I'm going to use my calculator here. So it will take me a minute. So 2 cubed divided by 3 star x 3. So the first answer, so first iteration I got is minus 0.323, right? Because I'm looking at accurate up to 2 decimal places, so I will just write 3 decimal places. So then I compute the next iteration. My next iteration is x2 is minus 0.3221. So now if I was, so in this case, you can already see that the second iteration is similar to the first iteration, and they are up to 2 decimal places. And that's what we were looking at. So therefore, x is minus 0.32, accurate up to 2 decimal places. So this is the setup of Newton's method. All right. So that takes care of Newton's method. Um, okay. So notice the following. Oops. Okay. So if notice that derivative of x square is 2x. Therefore, antiderivative of 2x is x squared. Yeah, so it's the exactly opposite of derivative. So how do I define it properly? So in this case, I will say, so if derivative of big function f is my small function f of x, then antiderivative of this small function f of x is this big F. Okay, so this is what the antiderivative concept is. Okay, so now for given f, find all f, capital F, such that f prime f equals to f. So this is the idea behind the antiderivative. So let's say, for example, I give you 2x. So this is your small f of x. Now, what is the antiderivative of this? So antiderivative of this guy is a function whose derivative is 2x. So, if you take f of x equals to x squared, then you can see that f prime x equals to 2x, which is the f of x. So therefore, antiderivative of 2x is x squared. All right. Now note that I can also have a constant, some constant c here. C is a constant. Then you can see that derivative of that again is going to be 2x, right? So therefore, antiderivative of 2x is x squared plus c, where c is a constant. Okay. So now let's do the following problems. So find an antiderivative of the following function. So f of x equals to x squared. So whose derivative is x squared? We do not know whose derivative is x squared right away, but we know that if you take derivative of x cubed, you get 3x squared. But you want basically derivative of what? You want antiderivative of 3x squared. That means you're looking for a function whose derivative is x squared. So divide both sides by 3. You have x squared. So if you bring it inside, the derivative, the constants have free pass to go inside and outside the derivative. So d by dx of x cubed by 3 is x squared, right? So find an antiderivative. So an antiderivative means any antiderivative. So we get that antiderivative of x squared is x cubed by 3 and plus c if you want, right? So there are many antiderivatives of given function, right? Because if you keep changing the constant, all of them are antiderivative. So now let's look at the following. F of x equals to 1 over x. So whose derivative is 1 over x? So we know that derivative of ln of absolute value of x is 1 over x, right? So therefore, antiderivative of 1 by x is ln of absolute value of x plus c. So this is what antiderivative of 1 over x is. Yep. Now let's look at the following problem. Show that all the antiderivatives of f of x, which is x to the n, and not equal to -1 is given by the following. So to show that this is antiderivative of x to the n, all you need to do is compute f prime of x. So let's look at f prime of x. That is going to be 1 upon n plus 1. The constant comes out. Derivative of x to the n is n plus 1 times x to the power n plus 1 minus 1. And derivative of constant is 0. So you get n plus 1 upon n plus 1 times x to the n. And these are not 0, right? Because n is not -1. So you have x to the n. Therefore, you can see that antiderivative of x to the n is x to the n plus 1 upon n plus 1 plus c. Of course, when n is not -1. However, when n is -1, you have already seen that case here. So when n is -1, you will get antiderivative of x to the -1 is ln of absolute value of x plus c. Okay. So let's go back to the formal definition. So a function f is called antiderivative of a small f on an interval I. If you take the derivative of f, you get this small f back. So this is what the antiderivative is about. Okay, all right. So note that following, if you take any antiderivative of f on interval I, then the most general antiderivative is f of x plus c, right? Because adding constant, when you add a constant, you take the derivative, you get back your small f. So here's a table for antiderivatives formulas. So basically, if you're, so the notation is the following, antiderivative of g of x, suppose is capital G of x, then antiderivative of c times g of x is going to be c times g of x as well. If we have antiderivative of small g of x is this capital G of x, and h of x antiderivative is this big H of x, then if you take antiderivative of g of x plus h of x, it's going to be capital G of x plus h of x. This we already saw. This we already saw. Now derivative of e to the x is e to the x. So therefore antiderivative of e to the x is e to the x as well. Now derivative of sine is cosine. Therefore, so derivative is of sine is cosine. Therefore antiderivative of cosine is sine. Similarly, derivative of cosine is minus sine. So this we can see separately. So derivative of cosine x is minus sine. So if I multiply both sides by minus sign and bring the minus sign inside, I'll get this. So derivative of minus cosine is sine x. So therefore antiderivative of sine x is minus cosine x. Derivative of tan x is secant square x. Therefore antiderivative of secant square is tan x. Derivative of secant x is secant x tan x. So therefore antiderivative of secant x tan x is secant x. And the list goes so on and so forth. Okay. So these are the formulas for, so again, you basically understand antiderivatives using derivatives, right? At least to start with. So let's find all the antiderivatives of this function, f of x equals to x cubed plus 3 square root of x minus 4x squared. Now note all of these are powers of x. So we have, I can write it as x cubed plus 3x to the half minus 4x to the minus 2. So now what are the antiderivatives? So antiderivative of f of x. So this is going to be f of x. Now go back to the power rule. What power rule we have for the antiderivative? If it is x to the power n, is going to be x to the n plus 1 divided by n plus 1. So you add 1 to the power and divide by that, add extra 1 added power. So here it will be x to the power 3 plus 1 divided by 3 plus 1 plus 3 times x to the power half plus 1 divided by half plus 1. Then minus 4x to the power minus 2 plus 1 divided by minus 2 plus 1. Then plus c in the end to represent the most general antiderivative, right? To find out all the antiderivatives. So here we get x to the power 4 by 4 plus 3 times x to the power 3 by 2 divided by 3 by 2, that is multiplying by 2 by 3, minus 4x to the power minus 1 divided by minus 1 plus c. So this is your antiderivative already done. If you want to simplify it further, please go ahead. So the simplification would be c. So this is how the antiderivative is basically. Now, suppose you have f is the following function, f prime equals to 2 cos 3t plus 5 sine 4t plus e to the power t. Now we know antiderivative of, so we know antiderivative of cos t, right? So antiderivative of, so that we know by the following, because derivative of sine t, again we are taking derivative with respect to t, Derivative of sine t is cosine t. So what is the antiderivative of cosine of 4t? So for that, or cos of 3t. So let's see. So if you look at sine 3t, the derivative is going to be sine cos. So derivative of sine 3t is going to be cos 3t multiplied by 3. So we get derivative of, divide both sides by 3, and the 3 can come inside the derivative, is going to be cos, right? So the antiderivative of cosine 3t is sine 3t usual, but instead of multiplying by the coefficient as you do in the derivative, you're dividing by the coefficient. So, so we have what? So let's see, f of t is going to be 2. What is antiderivative of cosine is sine 3t divided by 3. Similarly, antiderivative of sine 4t, so sine t is minus cosine t, so it's going to be minus 5 cosine 4t divided by 4. Plus 3 will come out as a constant. Antiderivative of e to the t is e to the t. And then plus constant, a big constant c to represent the most or all of the antiderivatives. Now this is your function. So this is f. Now let's look at part 2. It says which of these satisfies f of 0 is 0. So let's look at f of 0. So on one hand, f of 0 is 0. On the other hand, when you substitute in your function, you get 2 sine 0 by 3 minus 5 by 4 cos 0 plus 3 e to the power 0 plus c. So we get what? So sine 0, this has become 0. So we have 0 equals to minus 5 by 4 plus 3 plus c. So therefore, c equals to what? C equals to minus 5 by 4 plus 3, which is going to be 12 minus 7 by 4 with the minus sign. So this is your C. All right. So let's look at the following problem. So f double prime is equal to this guy. F of 0 is 3 by 2. F prime of 0 is 1. Find such an f. All right. So first of all, what is antiderivative of e to the power minus 2x? So let's look at the derivative of e to the power minus 2x. That is minus 2 times e to the power minus 2x, right? Using chain rule. So divide both sides by minus 2. So this will cancel off. So you see that antiderivative of e to the power minus 2x is e to the power minus 2x divided by minus 2. Yep. So we'll use that here. So we have f double prime. So first step would be to find f prime. So f prime x is going to be 2. Antiderivative of e to the minus 2x is e to the minus 2x divided by minus 2 plus what is derivative of 5 is going to be 5x plus c, right? Because what derivative of what is 5? Derivative of 5x is 5. So therefore antiderivative of 5 is 5x. So we got this now. Now there are two options. Either we can go ahead and find f by taking antiderivative again, or we can find out this c by substituting what value we have. So we are given f prime of 0. On one hand, it is 1. On the other hand, this will become 2 divided by minus 2 plus 5 times 0 plus c. So I get from here, this will cancel out, will give me minus 1. So c equals to 2. And my f prime x then looks like e to the power minus 2x. Oh, nobody corrected me here because this 2 and this 2 will cancel out. So I'm left with what? I'm left with e to the power minus 2x plus 5x plus c. Sorry, nobody can correct because people are muted here. So what is f prime of 0 going to be? In this case, it's going to be, well, the answer is still the same. We have minus 1. So the answer is indeed the same. So we got f prime x as e to the power minus 2x plus c, sorry, plus 5x plus 2. Now let's take antiderivative of this. This is going to be f of x is going to be antiderivative of this. Let's see what is the problem. That's right. Thanks. Now f is again antiderivative of this, which is going to be e to the power minus 2x divided by minus 2 plus 5. What is derivative, antiderivative of x squared? Is x to the power, this is x to the power 1, so x to the power 1 plus 1, which is 2, divided by that power plus 2x plus d. Now we need to find out this d. So for that, the extra piece of information is given to us. So f of 0 is going to be plus 1 by 2 plus 0 d. And on the other hand, I'll get what? 3 by 2. So therefore, d equals to 1. So therefore, what do I get? F of x equals to e to the power minus 2x divided by 2 plus 5x squared by 2 plus 2x plus 1. So this is the antiderivative